Hello, my name is Call, and this is my video for the Maze and Monsters project for GPE303. Alright, now let's start off with the AI. First, we have the nav mesh, which is just the baked-in Unity nav mesh, to where it goes, it looks at the target, and then it just animates itself and moves and avoids obstacles. Next, we have the breadth first, which creates a class for nodes, and then it goes through checks and just starts off at the starting node and just creates a path to the target end node, and then follows that path. And it creates the path before it actually starts moving, of starting the node, creates no connection, creates a list, open, close list, adds the start node to the open list, and then it just starts running through the nodes and their connections till it reaches the target node. And then when it does, it goes and just starts moving towards the target node, which starts moving through the list. Now, for the first manipulated AI, we have the other, which this one is a simple one of it goes in, and whenever it runs into a problem, it turns left. Does this by using AI similar to obstacle avoidance, but instead of, when it can't move, instead of rotating a positive turn speed, it rotates a negative turn speed. So whenever it runs into an object, it turns left, continues running, and then when it doesn't see the object anymore and can move forward, it moves forward and starts turning to the target node again. So it'll keep turning left whenever it runs into a problem. Next up, we have obstacle avoidance, which this is another simple one, to where it basically just it gets the target end position, it looks at that position, it moves at the set speed, it moves forward at that speed. If it runs into something, it changes to a turn to avoid state, and that state has it rotate right at a set turn speed, so it can move forward again. Then it changes back to goes to the move to avoid state, and then in the move to avoid state, it starts moving forward till a set time is up that it thinks it's gone far enough. Then when it's done, it goes back to the regular state, which has it start running towards the target, and thus it repeats the process. And how it checks to see if it hits something, it does a sphere cast with the ray gets its current position and gets its forward, gets its distance to turn, gets the hit info, gets its speed, and then checks the game manager to check whether that node is a node, a movable path, or not. If it's not a movable path, it'll return false. Otherwise, it's movable, it'll return true. For Dijkstra's, it's similar to the breadth first, But when it when it starts, it creates the list, and it does this by checking each and every node. It starts off with what's the available nodes around me, adds those to the list, then what's those available nodes, continues on, and then every single time it checks the list to find the smallest element, and then it'll add that to the list, and then it'll go find the next smallest element. So, and it does this by checking the list and checking the nodes its target, and then the connections it has, and it's and it sets out to find the smallest amount of nodes possible to go from the starting node to the end node if they all have the same weights. And it keeps checking to where is a node open? Yes, add that. If it's not the lowest, don't add it, continue on. Then when it finishes the list, it'll check to see whether they found the goal or not, if the goal is somewhere on the list. Then, after every node's been added to the list and the goal's at the end of the list, and your start node's at the beginning, it'll then iterate through the list to find the smallest obstacle it can. And it does it by starting at the beginning and then checking each connection the nodes have with the one next to it, and goes and it adds the cost of the nodes, and then it starts off at the current node, which will be your start point. Then it finds the connection to that, adds that cost, then it'll find that connection, add that cost, and it'll continue on. And then when it's done, it'll return your smallest node and your path cost, and if it's the smallest, it'll start moving. If not, it'll go to the next node, start at that one in the list, and check its connection. So if you have two openings, so in the thing you have an opening here and here because this one's blocked, it might start here if this is the first node in the list, check this connection path here, and then it'll check this one and figure out what's the smallest before it goes. A star is similar to Dijkstra's, except when it checks the cost, it doesn't use the singular path cost that Dijkstra's uses of just an overall path cost that's the end all of it. What it does is it has G, H, and F as the standard variables, where G equals the connection cost, H equals the distance of the whatever the current node is to the target node, and then F equals G plus H. Then it goes through, checks, records those, then it goes, iterates through the list again. If F, G, or H, any of those is lower than the previous round, that's the new smallest cost. and then it'll iterate through the list again till it hits all connections to the starting zone, because you have your first node here, then you have these 3 nodes, which are all connections. They're separate connections that it can go. Then you have those next to it, and it continues on and on and on till it finds the smallest path. This is generally regarded as better than Dijkstra's for doing this, because Dijkstra's just has the one singular path cost. Whereas when you're doing A star, you can write out the algorithm yourself and get it as close to smallest as possible versus Dijkstra's sort of large brushstroke. Now let's see all these work. You have the maze, which you can create yourself. You can bet on which monster you think's gonna win. And then you can start the race. If we see here, we see nav mesh and breadth first moving. We have obstacle avoidance, which is just running forward. And you can add stuff in there to change it. Yeah, we have obstacle first, which is just moving off. We have the other, which just keeps moving left. We have Dijkstra's and A star, which are both following different node paths, because Dijkstra's is whatever's the first to get there and is the smallest overall with the connection. A star is connection plus distance, so you can see the difference there between which one will get there first. And that's it. Thank you for watching. Bye.